Bueno, buenos días. Bonjour. Tenemos invitados franceses que van a ser parte de la evaluación de la tesis de Franco MOLINA. Hoy estamos para la defensa de la tesis de Franco. Primero que nada, agradecer al tribunal y en especial a la evaluadora externa, la doctora Carolina Lorente, que es investigadora principal en el área de química física. Su especialidad es fotofísica, fotoquímica y fotosensibilización. Su tema de trabajo es estudio de los mecanismos oxidativos involucrados en el daño de biomoléculas durante procesos fotosensibilizados por pteridinas, búsqueda y caracterización de antioxidantes naturales para la prevención del daño oxidativo. Well, we are here today for the defense of the thesis Franco MOLINA. We want to thank the presence of the tribunal from France, Dr. Nicolas Neuhaer from the University Paris Nord, Sorbonne, and also Philippe Maitre from Université Paris-Saclay, and the Dr. Gilles Reward, which is in video conference. Many thanks. Also, we want to thank to the tribunal that have followed the thesis along this time. Dr. Laura Moyano, and Dr. Liliana Jiménez. Many thanks. And also the external evaluator, Dr. Carolina Lorente from University from La Plata, from the Institute INIFTA, CONICET. Dr. Carolina Lorente is principal research in the chemical physics area. His specialty is a study of oxidative mechanisms involved in the damage of biomolecules during photosynthesis processes by pteridines, search and characterization of natural antioxidants for the prevention of oxidative damage. Well, again, many thanks to all. I will continue in Spanish in order to read the documents from the thesis. En la ciudad de Córdoba, a los 23 días del mes de septiembre de 2025, siendo las 10 horas, en la sala de conferencias del edificio integrador de la Facultad de Ciencias Químicas de la Universidad Nacional de Córdoba, se reúne la comisión evaluadora de la tesis de doctorado, modalidad cooperativa, cotutela, el licenciado en Química Franco Leonardo Molina, integrada por el doctor Philippe Metre, presente por videoconferencia, la doctora Liliana Jiménez, la doctora Elizabeth Laura Moyano, la doctora Carolina Lorente, en carácter de evaluadora externa, presente por videoconferencia, el doctor Nicolás Neuhaer, en carácter de evaluador externo, a los efectos de la evaluación final del trabajo de tesis de doctorado en Ciencias Químicas sobre el tema espectroscopía de iones fríos de relevancia biológica desde radicales cationes de nucleobases a aniones fotodonores de monóxido de nitrógeno, realizada en el Instituto de Investigaciones en Físico-Química, Departamento de Físico-Química de la Facultad de Ciencias Químicas de la Universidad Nacional de Córdoba, y en el Instituto de Ciencias Moleculares de Orsay, Universidad Paris-Saclay, bajo la dirección del doctor Gustavo Pino y del doctor Gilles Gregoire. La comisión de tesis ha considerado previamente que el licenciado en Química, Franco Leonardo Molina, ha cumplimentado con los requerimientos estipulados en los artículos 2 y 26 del reglamento de la carrera de doctorado en Ciencias Químicas. En este punto vamos a comenzar a escuchar la defensa de Leonardo de la tesis denominada Cryogenic Ion Spectroscopy of Biologically Relevant Ions from Nucleobases, Radical Cations to Nitrogen Monoxide. Okay.
NO photodonors.
NO photodonors. Yes. Thanks.
Thanks to you. Thanks, Marcela, for the introduction. Thanks to everyone actually here today. It's really nice to share this presentation with all of you. So, as she already introduced, this is the main topic for my thesis project. Has been done in international co-tutel between two universities, the University Paris-Saclay and Universidad Nacional of Córdoba, under the supervision of the Dr. Gustavo Pino and the Dr. Gilles Gregoire. So, first of all, let me introduce some backgrounds regarding this subject. We are going to talk about spectroscopy and ions, yes, when we have some biological interest on them. So why we're interested in them? Because we know we're interested on the interaction of the light with the biological system. When we think on this, we are wonder about how this interaction works and how it could be useful for us to understand it. So for example, because we know that the light is central for the life. For example, here we know that it's crucial from the origin of the life, just from the DNA and RNA basis, to sustain the biological processes that could be the photosynthesis, which is a process that helps us to transform, yes, a photon energy into a chemical energy. So in all this process that we are going to discuss, the main aspect is the absorption of a photon. Because we notice that is a precondition for any photochemical reaction, any photobiological phenomena that we are interested in. And this process of the absorption of the photon is carried out usually, in this case, for the UV chromophore. In the UV chromophore, it's that molecule or moiety or structure which is responsible just to absorb, for example, the sunlight and transform it into a chemical energy. So, as a main goal in the thesis, we want to understand the photoinduced process and photoreactivity of biologically relevant ions. In this case, for example, first we wonder about what are the chromophores that we have to look at. If we think on the DNA strand, we could observe that this is the structure, but the main structure of this DNA strand could be, if we think on the chromophore, are the nucleobases. We have 4 nucleobases: adenine, thymine, guanine, and cytosine. So when we are thinking now in the interaction of the light with this DNA strand, we could think, for example, what happens when we have some diagnostic of radiotherapy, because in this case, we are using a light like this one, when we have X-ray or X-gamma, yes, energy, which will induce an ionization of the nucleobases. This ionization is going to remove an electron from the nucleobase, and as a consequence, we are going to change the electronic configuration. This change in the electronic configuration is going to modify the photoreactivity of these nucleobases, because now we have a radical cation. The presence of these ionized nucleobases is, we are wondering because it could disturb the hydrogen bond in the DNA strand, as well could modify the structure, the chemical structure of the nucleobases. For example, here we could observe different tautomerization processes. And finally, what we are going to obtain is that an instability on the double strand DNA. Okay, so finally, what we are going to have a genomic damage of the biological system. But well, here we are thinking in the light as we are going to change the photoreactivity of the molecule, and we are going to have an undesired condition. But what happens if we think now how to use the light to control the photoreactivity on a molecule and generate a therapeutic application? For example, in this case, we are thinking on use NO photodonors. These NO photodonors are molecules which are able to absorb the photon, the visible photon, and just release NO after the absorption of the photon. And here we notice that if we are able to introduce and control the NO concentration in a biological system, we could, for example, increase the NO concentration in the biological system and induce some antitumorigenic effects. It could be used, for example, for cancer treatment. So here we are interested on use the light as a trigger to control the NO concentration, for example. In all these processes, when we are thinking about photoreactivity and photoinduced processes, we have to think on the photophysics and photochemical processes in the aromatic molecules that we are going to study, for example. This is the general scheme. Here we have electronic energy, and here we have the nuclear coordinates. These nuclear coordinates are the coordinates that are going to build your molecule. We have a set of different atoms that are going to define these coordinates. So what happens when we have an absorption on the whole? We first start from here, the S0, something that we call it a singlet state. This is the minimum quantum energy state that could observe in the molecule. So then when the photon is absorbed, we are going to promote the system to, for example, here S1 state. This is an electron excited state of the system. This excited state is unstable because we have an excess energy on the system. So as a consequence, the system is going to try to dissipate this excess energy. And there is many mechanisms. But here, for example, we could distinguish the radiative and non-radiative mechanisms. The radiative mechanisms are the phosphorescence and fluorescence. All this process, what I'm trying to do is just to dissipate the excess energy and return to this configuration. Then as well, we have the non-radiative mechanisms, as will be, for example, here, vibrational relaxation, intersystem crossing, conical intersection, or internal conversion. In this point, for example, in internal conversion, we could think as well that a photoproduct could be generated. Photoproduct is just generated as consequence of the photon absorption. So here we could think that we could generate, for example, photofragments. And in this case, if we follow or we are able to measure somehow the photofragment, we could follow the absorption of the photon. So in this case, we know that we are going to the gas phase UV visible, for example, spectroscopy help us to understand all these intrinsic properties in the molecules that are going to help us to understand how we are able to play with this photoreactivity or photoinduced processes. Here, the technique that I'm going to show is the action spectroscopy. In this case, for example, the action spectroscopy is a technique which we have a configuration in the ground state. We are going to absorb a photon, and as a consequence of this photon absorption, we are going just to generate photofragments. Okay, where the system is going to dissociate, just following internal conversion or direct dissociation in the excited state. So here, all this technique has been well used for example, gas phase spectroscopy in neutral molecules, but now we are interested to study the ions. In this case, we are going to show you how we use the cold ion spectroscopy to study them. Here in the cold ion spectroscopy, we are going to combine laser spectroscopy and mass spectrometry, which are those two techniques. The advantage of to use this technique is that we, for example, here we have, this is the commonly excitation of the system that we are going to have, for example, in room temperature. But if we are able just to cool down the system and reduce the internal energy of the system, we are able to minimize the internal energy to the minimum ground state energy. So here, as a consequence, in the spectroscopy, we are going to observe a broadband, which is, for example, in red for the cool system, the hot system, from the warm system at 300 kelvins. And when we are going to cool the system, we are going to enhance the resolution of the spectrum. As well, other advantage is that, for example, if we have a large isomer population, we are going just to observe the most stable configurations. And finally, since we have a high resolution byronic spectra, we are able to compare directly with quantum chemical calculations. This is the main setup that we have used during my PhD at ISMO. So let me introduce the different parts that are here and highlighted. This is the source. Here from the source, we have, for example, here we have the electrospray ionization source, which help us to just start from a solution and transfer the ions from the solution to the gas phase, just injecting through a needle to the gas phase here. Inside of this system, we are able just to transfer, for example, all the ions to the following chamber, which is this one. We usually call it cluster trap. In this trap, we are able, if we are interested in, we could build water molecule complexes. We could add some water or methanol, for example, molecule just to add some solvent molecules to the ion that we are interested in. Then we have this linear polypole, which help us to just to define the mass that we are interested to study. And the main study, all the cryogenic process that we are interested to carry out, it's going to occur here in the QIT. The QIT is already cooled at 10 kelvins. So here, when the ions are coming directly from here, we could trap the ions here and store the ions for a few milliseconds, for example. Inside of this trap, then we are able to extract all the ions, and detect them through the linear time-of-flight mass spectrometry. As a consequence, we could record the mass spectrum. As well as mentioned before, we are able to perform a spectroscopy just shining a laser inside of the QIT. So when we shine the laser in this condition, we know that we are exciting a cold ion molecule. So the main advantage of use this setup is we are able to control the entrance channel of the spectroscopy that we want to do, because we could select in mass the ion that we are interested. Then we could control the excess energy of the system, because we are able to define the photon that we want to shine. And finally, define which fragmentation of which fragment we are going to follow in the mass spectrometer. So as mentioned before, we combine photodissociation spectroscopy, and this is how we just record, for example, the absorption of the photon. We have the system on the ground state, we record the corresponding mass spectrum, we excite the system. This system is in an electron excited state. We're going to dissipate the energy and just generate a fragment. This fragment is going to be observed, for example, here with the mass spectrum. Here we have the fragment A, and here is the parent signal. If we perform the subtraction of these two spectrum, we could plot, for example, here, the photo-induced dissociation mass spectrum, which we call it PID. It's going to show in positive values the photofragment, and in negative values the complex, or the parent ion that we are studying. So the UV visible photodissociation spectroscopy that we are going to show in all these results, it's mainly is going to be used to study the electron excited states. We are usually use one color excitation. It means that we're going to use UV or visible energies. And to record, for example, this spectra, we just going to plot this parameter which follow the intensity of the photofragment that we generate as consequence of a photon absorption, and the intensity of the parent. So finally, if we plot the fragmentation yield, which is this parameter in function of the laser energy, we are going to obtain the corresponding spectrum. Then I mentioned that we are going to compare all the experimental data with theoretical calculation. Here we have quantum chemistry calculations, and I'm just in general view, we are going to always perform geometry optimization, frequency calculation of the different electronic states, because we are interested on to study the ground state calculations, for example, just to perform the infrared spectrum and to perform an isomer assignment of the molecule that we are studying. And then in the excited state calculation, we are interested to perform an electronic excitation assignment, just comparing the electronic excitation for the vertical excitation or the Frank-Condon analysis. Usually, the method that we are using is the DFT, TDFT, and CC2 level, which are below here. So, well, one of the main topic of my result is the nucleobases silver complexes and nucleobases radical cation. In this system, we are interested to study the radical cation because we know there is, as I mentioned before, we could ionize the nucleobases, and as a consequence, we could obtain this radical, but we noticed there is lack information regarding this system. So we will wonder how to study these radical cations. One of the approach that we observe in the bibliography, this is a really a wonderful study performed by Francis Tureczek. They start of a copper complex of the nucleobases you are interested. For example, here is cytosine, and then they are able to use the CID, which is collision-induced dissociation process. It's just going to dissociate the molecule. And as a consequence, you are going to generate the radical cation, this one, the cytosine, for example, in this case. After that, they show how to study this system performing action spectroscopy, as shown here, following different fragmentation channels, and they obtain the corresponding infrared spectrum. And combining these two techniques, they show how they are able to assign at least a set of 4 isomeric forms of the radical cation of cytosine. It's important to notice that in these works, they use, all of them has been performed at room temperature. So here we are interested to use the cold ion spectroscopy just to enhance the spectral resolution and achieve, for example, an isomer selectivity on the experiment. So, here, what is we are proposing? Here we propose this strategy to study the radical cation. This is all proposed. To start first from several complexes, all this strategy has been characterized previously in our group, the Gustavo Pino and Gilles group. So here we combine, we are going to use these several complexes just to excite it, for example, with the UV photon. We are going to promote the system to an electron excited state, which has a charge transfer process. An electron from the nucleobase is going to be transferred to the cation of the silver, and as a consequence, we obtain the radical cation that we want to study, for example. So then we propose to isolate this radical cation and perform action spectroscopy, as mentioned before. So in experiment, how we work with this? First, we identify the silver cytosine complex, which is trapped here in the QHE, cooled, and then extracted. Then we shine a laser to photodissociate. We identify the photofragment, for example, here, which is the main fragmentation channel. We identify is the radical cation of this complex, so it can be useful for our goals. Then we isolate this radical cation, and we could perform the spectroscopy, the action spectroscopy on this radical, just performing the dissociation. So at this point, it's interesting to notice that we are going to use, for example, two lasers, one to dissociate the complex, another one just to perform the spectroscopy. Then, this is the spectrum that we usually obtain, for example, in the silver cytosine complex. This is the UV photo UV photodissociation spectroscopy. We identify that there is a set of two bands, one band A around 32,000 and band B around 35,000 by numbers. And then at this point, we're wondering about what are the isomers that could be populated under our experimental condition and could be assigned to the spectra, and as well as, or if correspond to a specific isomer with different electron excited states. So these are the two main concerns. To reply these two main concerns and assign firmly this spectrum, we are going to perform conformal selective spectroscopy. The conformal selective spectroscopy that I'm going to show is the RUV deep spectroscopy. In this case, we are going to use two lasers. The laser, for example, here in the UV, we are going to fix it in a specific band, band A or band B. And delay in time, we are going to scan the infrared laser. In consequence, we are able to obtain an infrared laser which is going to be specific of each band. So in this case, for example, we are going to observe this kind of the spectrum when we are going to just observe a dip in the photodissociation signal created for the UV laser as consequence of the depopulation of the ground state through the infrared laser. It creates a dip in the photodissociation signal. The spectrum that we could record are in this way, for example, for the RUV deep spectroscopy. Here is the infrared spectroscopy for the band A and band B. As we could notice, there is really differences on the infrared transition. So now we're wondering what are the structures responsible of these infrared transitions. In this sense, we perform theoretical calculation. We explore different conformers of the silver cytosine complex. We identify the lowest structure and we compute the infrared spectrum. All these spectra then are compared with experimental data. And as we could observe here, we have a set of two ketoamino forms of the cytosine and two enolamino forms of the cytosine nucleobase, which presented the cation of the silver in different positions. But if we just compare, we could identify that the two ketoamino forms could be easily assigned to the experimental data. The ketoamino form 1 could be assigned to the band B, the black trace, and the ketoamino 2 could be assigned to the red trace in the band A. So after to identify the conformer, we are now to study the electron excited state of these silver complexes. We could identify that, for example, performing a CC2 level calculation, that the pi-pi transition, which is the first pi-pi transition of the systems, are close to the bands that we observe in the experiment. For example, in this structure, we observe this one is really close, the adiabatic energy really close to the band in the experiment, while this pi-pi transition, the adiabatic energy is close to the red band. In this sense, we perform an assignment of this electronic transition. So the general picture that we obtain is like this one. We have two structures in two different bands. After that, we are wondering now what happened. We generate the radical cation at this energy or this energy. So we notice that when we generate the radical cation in this band located at 32,000, we generate a radical cation which by Brownian spectroscopy looks like this one. We observe a broad band around 70,000 wave numbers. But then when we generate the radical cation in the band B, which is the black trace, we observe another Byronic signature, which is a sharp transitions around 24,000. So from this point of view, we know that at this point we're suspicious about there is two tautomers present when we generate the radical cation at different excitation energies. So to assign this structure, we obtain again the double resonances infrared spectra, and we compare with theoretical calculation for the open shell species. So here we are comparing, for example, the experimental data obtained for each band of the radical cation with the theoretical calculation of these isomers. And we could identify the same keto amino forms that we recognize in the silver complexes. So finally, after that, we are interested to perform an assessment of the electronic excitation of this system, because the main challenge of this system where we are going to study the electronic excited state is they are open shell systems. So they are radical. It could be, for example, a spin contamination, and it's really challenging to study the electronic excitation. But surprisingly, we use TFT calculation, and we identify that the pi-pi transition of the keto amino form 1 could be optimized and compared with experimental data, and as well the first pi-pi transition of the keto amino 2 could be is close in energy to the experimental data. After that, we perform Frank-Condon simulations, which are going to provide us the vibronic signature, the vibrational signature in the excited state, and we could compare with this visible with the vibronic experiment. And as we could observe, we have a good simulation compared with experimental information. So here we could observe and we could firmly assign the electronic transition of these isomers. So finally, with this study, we could show that the use of a silver nucleobasis complex could be used to generate the radical cation, and then study the radical cation through cryogenic ion spectroscopy, as well that the resolution of the cold ion spectroscopy help us to perform a tautomer selective experiment or isomer selective experiment. And finally, as well, we could identify uracil, and we could perform the same experiment and studies for uracil and thymine radical cation using 1 and 2 color spectroscopes. So now let me change to another system, the NO photodonors. Now we are going, as mentioned before, we are going just to now study another system with another purpose. Here, we are interested to, for example, have some therapeutic application using NO photodonor. So for here, we are going to identify at least 2 main specific objectives. The NO release has to be the main fragmentation channel as a consequence of the photon absorption, because we are interested to use it in this way. And then that the absorption of the photon has to occur in the biological transparency window, which is the energy region when any tissue or any layer of the biological system are not able to absorb the photon energy. So in this case, if we set the excitation energy in this region, then no photon donor absorption is going to be specific. So looking at the bibliography, we identified that the nitrophenolate derivatives, which are these anions. Here we have a nitrate and phenolate group. We could identify that these compounds are already described through action spectroscopy in cold ion spectroscopy, that they present a charge transfer process which is going to release NO. So after the absorption of the photon, they're able to release the NO, which is something that we want. And as well, the NO loss is the main fragmentation channel. But look at it, all this structure, we identified the meta. It's close to the biological transparency window that we are interested to tune the electron excitation of NO photon. So in this sense, we are going to use this model compound, the meta-nitrophenolate, just to perform following study on these NO photodonor systems. Here I'm just showing how we are able to reproduce the visible photodissociation spectrum following the different fragmentation channel. Here is the NO loss as one of the main fragmentation channel. And as we could observe, we have a well-resolved bands for this compound. So now we are interested to study the intrinsic properties of this anion and as well to tune the electronic properties at least in two strategies. One of them is using the microsolvation. The microsolvation implies just to build a water complex, just adding a one water molecule in this anion to observe what is going to occur when we add it. Then in the substitution effect, we are interested to add an extra electron donating group, for example, which are and test if the electronic property is going to be tuned as consequence of this extra substitution. So first, let me show you the microsolvation results. When we record the photodissociation spectra for the anion and the water complex, we clearly could identify a blue shift of the sharp transition. This blue shift now, it means that now the absorption of this water complex is it's higher energy. Yeah, we are quite far of the biological transparency window. So at this point as well, we are wondering, okay, what happened with this system? What is the structure of this complex? To understand the electronic properties, so at first we need to perform a conformer assignment. So we are going to study the conformer signatures that we could observe on this spectra, as mentioned before, following the conformer selective spectroscopy, which is similar to the RUV deep spectroscopy that I showed before. It means we are going to use a set of two lasers. Now we have, for example, a first laser, which is the blue one. We have a first laser we are going to tune and fix in a specific band. Here we fix it to the band origin of the visible spectrum that we are interested to study. And then now we are going to scan the visible, the second laser, which is delay in time. As consequence, we are going to have a double excitation. Now the depletion that we are going to observe is going to be related to the absorption of the both photons. So as consequence, when we compare directly these two spectra, we could observe that all the transition on the visible hot burning spectrum, which is here in red, are depleted. What it means for us? It means that there is just a single conformer, because otherwise we are going to observe, for example, that a few transitions are not depleted, but in this case, all of them are depleted. So we are exciting one conformer. We wonder which conformer it is. So we explore different configuration of the water complex, and we have, for example, these three lowest in energy structure: minimum A, minimum B, and minimum C. And finally, we were able to identify that the minimum A is populated under our experimental conditions. But to assign this, we have to compare RUV deep spectroscopy with theoretical calculation to firmly assign the structure. But this result I'm not going to show you today. I'm going to save it for question if you are interested, because are quite extent to explain that. For example, well, finally, we are interested to, as mentioned, to understand the blue shift. Here we observe that the minimum A is the responsible of the electronic absorption. Here, first, to understand the blue shift, we have to look at it, the molecular orbital energy. For example, in this case, we have the metanitrophenolate, which is the bare ion. This is without the water molecule. As we could observe, the electronic density in the ground state is located over the aromatic ring and the phenolate group. But when we promote the system to the excited state, this electronic density change to now part of the electronic density is located on the nitric group. This process is usually called a transfer process, intramolecular, and it's something characteristic of this system, which are quite, we call it usually push-pull systems. So when we look at this, we could understand what happens when the water molecule is added to the anion. Since in the ground state, the electronic density is on the phenolate group, when the water interacts with this group, the interaction is going to be strong, more stronger than in the excited state. As a consequence, the ground state is going to be more stabilized than the excited state, and we are going to observe the blue shift that we observe in the experiment, because the energy gap here increased compared to this one. So through infrared spectroscopy, as mentioned before, we were able to characterize the structure in the ground state of this complex, and we identify this strong interaction is something that we call it ionic hydrogen bond. It's more strong than hydrogen bond. So, well, from this point of view, with this study, we just studied microsolvation effect. We identify that we are going to observe blue shift, that which move slightly outside of the biological transparency window of the absorption of the anion. And finally, we could understand what happened with the blue shift, which has been reported. So now we want to understand the substitution effect using electron donating groups. In this case, this is the metanitrophenolate I showed you before, but now we are going to tune the electronic properties, just adding an electron donating group, for example, in position 2 and 4, using a methyl or an amino one. So here we have, for example, the structure of the methyl and amino anions with the substitution in position 2 and 4. We perform the visual photodissociation spectroscopy of these anions, and here is all these results. Here we were able to follow the visual photodissociation of this anion, just following the no-loss fragmentation channel as the main fragmentation channel, sorry. Here, just to analyze this, the influence of the different electronic donating group, function of the different position of the aromatic ring, we are going to compare the electron excitation of the visible bands with the band origin that we know for the metanitrophenolate without the substituent. So, as we could observe, as soon as we include a donating group, we observe a broadening of the visible band. As well, if we introduce a methyl substituent, we observe a blue shift as we could observe here. But then, if we use an amino substituent, we could induce a red shift of the band. So from this point of view, we have two questions. What is the reason of the broadening that we are observing? Why now the spectrum looks broader instead to what result as shown before? And what are the reasons of the shift that we are looking at? First, the broadening. To rely on this, to discuss this, we rely on the geometry optimization of the different excited state. The main transition that we are going to look is the S0, S1 transition. So we perform electron excited state calculation to optimize the structure in the ground and excited state and compare the structure for this electronic transition. And we could identify that one of the main reasons for this broadening is the torsion of the nitric group. As we could observe here for the methylated one, the nitric group in the ground state is slightly twisted, while in the amino ones we have in the plane. But then as soon as we promote the system to the S1 state, we observe that the twist in some system increase or really change the geometry compared to the ground state with the ground state. As a consequence, we realize that the large geometry change between these structures is going to induce a bad Frank-Condon activity. This bad Frank-Condon activity is going to show the broadening that we observe in the visible photodissociation spectrum. Then the shift. To understand the shift, we just rely on the energy of the molecular orbital energy in function of the different substitution. So here, on the bottom, we have the HOMO energy, which is this pi transition that I already described. And on top, we have the LUMO, which is this pi antibonding orbital. So we are going to follow what happened with the energy of this orbital as soon as we include different substituents. As we could observe, for example, when here in red line, we have the structure already optimized in the ground state. So in some of them, for example, in the methylated ones, the nitric group is already twisted. But so in this case, we induce that the nitric stay in the plane. So here is the black lines. When we compare all the structures in the plane, we observe that the LUMO energy is almost the same. But as soon as we just induce a twisting of the nitric group, we observe that the energy increase, which is here in red, for example, in the methylated ones. So in this case as well, then we compare with what happened with the energy of the HOMO. In this case, as soon as we increase the strength of the electron donating group, we observe that the energy of this orbital increase. So as summary, we could observe the blue shift due to a steric effect of the methylated group on the antibonding orbital, because here the energy gap increased. But then with the amino group, the electrostatic effect just on the HOMO orbital are more important. So here we notice that we are going to observe redshift because we increase the energy of the pi orbital. And we could observe that the energy gap here is short. So at the conclusion of this thesis, we were able, just performing cold ion spectroscopy, we were able to study the intrinsic photophysical and photochemical properties of the ions with biological interest, just understanding the relationship between the structure and the photoreactivity of these molecules. Then, as well as we show how the cold ion spectroscopy is able to compare with the electronic excited state calculation and ground state calculation, using high level of theory or low level of theory. Then I could just mention some perspective regarding the system that we were studying. For example, for the photodissociation nucleoserial complexes, we still wonder about how the radical cation is generated. We are here, this diagram has been built just with theoretical calculations. We have the electronic excitation or the energy for the silver complex. And here we have the dissociation energy and an estimation of the threshold for the charge transfer process that we observe that generate the radical cation. We know that the energetic has to be like this, has to be an electronic excited state on the silver complexes higher in energy compared to the threshold to generate the radical cation. but we are wondering about what happened in the middle, in the dynamic of the silver complexes. From this scheme, we know that it could be extended to another aromatic compounds to study. For example, one of them could be oxybenzone, which has been now the subject of one of my colleagues, Juan Cruz. Then as well, we were able to compare the high resolution vibranic spectra of the radical cation as a benchmark for quantum chemistry calculation for open shell species. Let me mention that here, thanks to Majdi Holfash, to help us with the high level of theory calculation to understand what happened with open shell species. After that, regarding the meta-nitrophenolate compounds, we were able to study solvation and substituent effect, just observing that the NO photorelease is observed in all the cases. Then we were able to tune the electron excitation of the anions using different electronic donating group, using different electron donating groups. For example, the amino one show the red shift that we want. Then through this collaboration with Jacques Le, which is from Taiwan, we were able to study, as I mentioned, the ionic hydrogen bond of these radical cations. As a further purpose, we could wonder about how the clustering of these anions, just adding different water molecules, and to see how the electron excitation evolved as soon as we include 1, 2, 3, or 4 water molecules on the system. But then the main concern that we are trying to understand is how it works or how it induces the NO release, how the NO release perform this rearrangement of the nitrate group to release finally the NO. As we could observe here, these are high level of theory calculation performed for the neutron nitrobenzene. Here we observe that the process in the excited state is really challenged because we combine singlet excitation to an electron excited state, and then we have some dynamics to a triplet state to just photoisomerize the nitrate and release the NO in the ground state. So it's really challenged. But we are interested to study and understand what happened here for the meta-nitrophenolates. We start to achieve this goal at the end of my thesis, just thinking, for example, in pan-pro photon electron spectroscopy. Why this spectroscopy? Because if we want to study the dynamic relaxation of these anions, we have to understand how the electronic detachment process is going. We are going to use two lasers to perform the dynamic, and then we just change the delay between the lasers. And as a consequence, in the anions, we wonder about the electronic affinity energy, which is the energy we are going to detach the electron. This energy could be close to the proof wavelength. So as a consequence, we are going to lose the anion, and we need to follow another property of the system, in this case, the kinetic energy of the electron. So this is our really challenging experiment, but we are start to do some of them. During the last 6 months of my PhD at ISMO, we set this part of the experimental setup. Here we have the QIT, so the ions, or the cold ions, are just sent to this region. Here we are able to perform the detachment using lasers. Here we are going to, for example, shine a laser, visible or UV laser, to detach the electron, and the electron is going to be recorded perpendicular here on the top. And we could follow the kinetic energy of the photoelectron in function of these diagrams. So finally, just thanks to all the institutions that could help me to do this PhD, which to me has been wonderful to have this experience. from the Universidad Nacional of Córdoba, University Paris Saclay, the different institutions, as well as the institution who provide me the source to the fundings to do these studies in France. And then just to say thank to all of you, to all the institutions, from ISMO to the director, Thomas Pino, then all the CCF team, which is here, my PhD colleagues over there, all of them I spent wonderful days just sharing experiment beers. Then as well, the different service that we have, the machine shop, electronics, informatic, as well the doctorate school, to the INFIC here in Córdoba, to the director, Sergio Dassi, then the Centro Láser team, which is the team of Gustavo Pino, all my colleagues during these years, and all of you, which are friends from my degree, and then all the people from the CPA, which is really help us sometimes with experiment, and the physical department, as well as to my supervisors. Thanks for all these years following weekly all my results and my trajectory during these years, and as well to my PhD thesis committee, which is it's wonderful to have all of you here, and as well to Philippe and Carolina, which is by Zoom connected. So thanks to all of you, and I'm just ready for your question and your remarks regarding.
Well, entonces, we have some time for questions. Maybe we can start with the external evaluators. Doctora Carolina Lorente.
Yes, I am here. Okay, first, I would like to congratulate you, Franco, and your supervisors for the excellent thesis you have done, which elucidate aspects of the structure of excited state of relevant biomolecules. This is very important. We are studying, it's important to know the interaction between the light or the radiation, electromagnetic radiation with the biomolecules to understand topics of cancers and how to use their light to treat cancer or eliminate some microorganisms. So first, I want to congratulate you and thank your explanation because it was very clear. The experimental setup you have used is amazing. It's very impressive. I also think that the results are you have a lot of results. They are very well interpreted, and also they were evaluated from with theoretical calculations. So the work you have done is really nice. I have no questions about your work, but I have some curiosities I have to discuss with you. For example, you have wrote in your thesis, and also you have said that the calculations you need to explain the results were the simplest calculations, and you don't need it complex calculations. Why do you think this was? If this was because your experimental results, what do you think? How can you explain?
Yes, we always we think that the experimental result has the final answer. So we start always from low level of theory calculation using DFT or TDFT, and then we scale to CC2 level. So all the time at just step, we compare with experimental data, and we just define which are the most accurate in terms of energy, in terms of different parameters. So, for example, that was the case of the radical cations. When we compare the energetic for the radical cations in the excited state, we identify that the TFT works somehow. We don't understand how it works, but it is. But then we rely, for example, in another system that we need to increase the level of theory because sometimes TFT is not enough. And we just perform the CC2 calculation and we get better answers.
Yeah, perfect. For me, it was new that NO it can be used, nitric oxide can be used to treat cancer. I heard about this topic recently in another conference. So how do you think you can propose to your results to optimize or improve the anti-cancer therapy using all the experimental evidence? Because I understand that nitrophenolates are toxic or cytotoxic, no?
Yes, but it depends. Yes, so from that point of view, we are not thinking about, I didn't present anything regarding, for example, drug delivery, but for sure the compound has to be inside of a carrier or something that is able to deliver to the site that we are interested to perform the treatment.
This was my question. How do you think you can use this technology or these results to optimize or to improve treatment, no? Yeah, I can imagine that you need a carrier or something about, but okay, in any case, the results are relevant to understand the model and to use these results in a treatment, no? Okay, I have another, let me see, because I have some notes. Okay, that's all. I think the explanation was very good. And this is not my talking. It was very difficult for me to understand what you have done. But I think you have done a great job. And I feel you have passion about you have done. I understand you want to continue this research. So I have to wish you all the best for the next period in your career, and thank you.
No, thank you. I appreciate your time. Thanks.
No.
Okay. We can continue with the questions. Dr. Philippe Medved?
Yes, Philippe?
Yes.
Okay.
Okay, I thought that the other referee will talk before me. But it's...
Nicolas is here.
Okay.
Okay. Thanks, Philippe.
I'm so sorry. Nicolas, please.
Thank you very much for the presentation, which is very clear, very didactic, and to the point to read your manuscript. Very impressive results, very good interpretations. So I have only curiosity questions.
Yes.
I'm very interested in the microsalvation element.
Okay.
So first, from an experimental point of view, how difficult is it to stick this water molecule? How much signal do you get in the first trap? And which distribution of masses can you observe?
Okay. I will try to return in a second. I'll try to return quickly to the slide and show you how we work with the complex. So, Yes, for example, here, the water complex, as mentioned before, we build it here in the clustering trap. So we have to store the ion for a few milliseconds there. In this trap, we have helium pumping inside the trap, and we inject a part of water or methanol molecule. And just we could play with the size of the cluster and the population, just playing with the temperature. Usually we range about, for example, the lowest that I went, it was around 120 kelvins. I observed a population around clustering for 4 water molecules. But the intensity is always going down. The most populated was 1 water, then the second one, and then so on. Yes, it's that way.
So do you get sufficient signal to study 2 molecules, for instance? Or?
Yes. I mean, the signal is enough, and you could optimize to get a better condition. But yes.
Okay. And it's very interesting in that, because you have a huge effect of one molecule.
Strong.
Do you expect something more, which was second one, or?
Well, it depends where the water is going to be being. For example, if it goes to the second water to the nitrate, it's going to interact with the LUMO of the anion, and so in consequence, you are going to play with that energy. In that case, perhaps you stabilize that orbital, and you are going to induce a reduction of the band gap energy. Yes, sure.
And from a calculation point of view, you use a crest to get different conformance with the water molecule. How many conformance do you get
with CREST?
Yes.
Well,
which energy criterion have you chosen?
Well, CREST usually goes to perform anti-room temperature that I was using from 0, and the CREST is metadynamic algorithm that is going to explore the surface in function of the temperature. So as soon as we are increasing the temperature, you have almost all the population. In this system, if I remember well, it was around 10, 12 conformer, because as well you have to include the CREST give you not just playing with the rotation of the water and so on, and even the other side of phenolates, or even I got the structure with the nitrate interaction in plane, out of plane as well. So it's really sensitive CREST, but I never performed for cluster, for example, to increase more water molecules, just with one.
Maybe one last question with that is when you use a double resonance spectroscopy,
yes,
and you have these 2 conformers in A and in B.
Yes.
You use very, very advanced harmonic calculation.
Yes.
Try to separate these 2 conformers.
Yeah.
To identify that. So it's the general question about this identification. You say that you choose for the good agreement between the experimental spectrum and the calculated spectrum.
Yeah.
What do you exactly call this good agreement? How can you say that mean A is not there or is there? It's not super. And it's related to the timing question, maybe, where you have the 2 T2NO runners.
Yes.
I have the feeling that probably the 2 are there, and maybe you can discriminate between these 2 ones, but I'm not sure it's your conclusion about that. So the question is about what is this good agreement, and how far can you say that you have this conformant, not the other one,
well,
to make this attribution?
I will say that in the case of the timing, we are not. We propose. We are not sure which of these 2 rotamer could be the responsible of the electronic excitation, because the electronic excitation energy of the rotamer is from one to another one is not going to change too much. So it's really hard to rely on one of them. But then, and in this case, when we are just using, for example, radical cations, we are using high level of advanced spectroscopy, because for IUV deep spectroscopy we use 3 lasers. So we are on, let's say, almost on the limit of the techniques. But we rely with that, with the energy that we found for the electronic excitation, and even with the vibrational transition, it's enough to explain the experiment. But when we are thinking in the infrared spectroscopy and we compute this infrared spectroscopy, we have the harmonic and an harmonic approximation. So in the harmonic, we always try to, with the theoretical calculation, we try to go to the limits and say, okay, this is what we have to do, and we compare with the experiment. For example, in harmonic, we apply the scaling factor according to the method. And if we observe that is enough, not enough, but we are sure about the molecule that we have or the isomer that we have, because the signature, we have an OH stretching or NH stretching and so on, we tend to propose a correction of the scaling factor for these conditions. But then in the water complex, it was another story because, water complex with the methanitrophenolate, it was another story because in this case, the vibration, I have some slide of that. Can go there. In this case, the story, when we perform the infrared spectroscopy, we identify many transitions. So for the water complex, we expect just, for example, the transition of the free OH and the transition of the OH, which is binding to an ion, plus the CH stretching that we observe for the meta-introphenolate. But then, as soon as we observe, we have many transitions in the water complex. So at this point, when we perform the harmonic calculation, as we could observe on the right, there is not enough information about the vibrational signature, because in the experiment we observe around 5 vibrational transition, and in the theory we predict at least 4. So in this point, we start to think in the anharmonicity of the system. So when we perform the first anharmonic calculation, we identify that, okay, we are able to reproduce at least the number of the vibrational transition, but not the energetic at least. So at that point, then we go further and say, okay, we have to think about the anharmonic approximation that we are using. Perhaps it's not enough. And then start the collaboration with Jean-Le, which is a specialist on that. But it works in that way, step by step, comparing all the time with experimental data and see what is the best with the calculation that we could do.
Thank you.
No, thank you, sir.
Congratulations. Very impressive work.
Okay, thank you. A pleasure. Thanks.
We'll continue with the question with the comment.
Philip, do you
Okay.
go with the questions?
Yes. So hello. I don't know if you see the video. Good morning. I think you are in the morning.
Yeah.
Thank you very much, Franco, for the presentation. Good selection of slide, and overall, this is an added value as compared to the manuscript, which I read a few weeks ago. So it was very interesting. So as maybe some people in the audience don't know, we know each other not because you were on the campus of Paris-Saclay, but because we met once a year for your thesis evaluation committee. So we had many opportunities to talk to each other. I listened to you. I asked questions, tons of questions, probably too many. And I had always very good answer every year. So I was happy with that. So if I have some questions, it's always around the same thing. And so if you go back to your slide number 7, the experimental setup?
Yes.
7 or 8, yes. Okay. So I'm a theoretician. I did some experiments lately, but from what I understood is that the signals can change one day from one day to another. That the electrospray source is very sensitive to many parameters, and that you have this first round circle here where you have an octopole with pre-cooling, where you can pre-cool your ions so they collide with some gas, and then you trap the ions for a certain period of times at a given pressure, given temperature. So my question is that what are the sensitive parameters on the experiments, and what is the reproducibility of the experiments? How many data are you waiting for, very reproducible data, before saying, okay, this is a spectrum?
Okay. Yeah. Thanks for your question. Well, the first parameter that we always start is to stabilize the electrospray source, because as you said, it's really sensitive condition, and it could change not every day, but a few months. We have to really clean it to be sure that we have a good condition with electrospray. And how we test this? With the intensity of the ions that we observe in the mass spectrum.
Okay.
As soon as we get the highest or the most intensity that we could obtain, playing with all the parameters. First, source, we know that they are cooling. Then we try to play with some configuration along the source region. And then perhaps we could optimize a little bit just with some parameters in the QAT, but it's not the usual. But yes, the first part is the source, and we play just to get the highest ion signal. After that, when we get this, we just shine the laser and we observe the photo fragments. And we record. I usually record the spectra, defining the photo fragment that I want to follow, and I observe the resolution that I got. If I consider that the resolution in 3 scans and taking an average of these 3 scans is not enough, we try to get back to the solution, to the source. Okay, it tries to increase the ion signal from the source, and then again to perform the spectroscopy. Okay. And finally, we decide which are with the highest quality or high resolution on the spectrum.
Okay. And regarding the isomer population, in one of the first slides, I don't remember which one, you are mentioning that 2 isomers are at play. Did you try to play on this isomer population? Try to decrease one population to increase another one? To make sure to cross this information with the IRUV, for example?
To play from experimentally?
Yes.
No. Because in principle, we think that the population is, in terms of the backgrounds of the electrospray, the population which is on the solution should be transferred to the gas phase. At the end, we start to think that perhaps the electrospray ionization condition could play some role in the population of the isomers. But I never play with that. I just read an article regarding that, and I get interested, but it was quite late for the testing.
Okay. Well, that's it. This was my question. So again, I would like to thank you, Franco, thank Gilles and Gustavo for inviting me to this defense. And that's too bad that I'm not there in Cordoba, which I stayed there once only, and it would have been a pleasure to join you today, but it was unfortunately not possible. Thank you again.
Thank you too.
Thank you, Benita. We'll continue with the question from the committee, Doctor.
In my case, no question. Just I would like please speakers congratulate you and your directors. Nice work. Also, I feel the same that say the that you have done the work with passion. Yeah, I feel the same. Also, when you with very patient sent to me the answer about the manuscript thesis. This manuscript was also very clear, even for me, that I have not specialist in this area, and also was very nice to read the manuscript. And this presentation of this was very nice. It was very clear, and so I would like to say that congratulations for you and your future. And I think you have a very nice future.
Okay, thanks so much.
Dr. Jimenez.
Thank you for a very clear presentation. I feel like the back student here in this thesis because it was hard for me also to understand all the thesis. But congratulations, a lot of work. You just can see that. And it's difficult to travel every year and to leave this path. Yeah, I know, I understand, I know that situation. It's a challenge for you. And congratulations also for your supervisor and yeah.
Thank you. Yes, I'm happy. I don't have to look like that. Give me.
I know.
Okay, we have some minutes from questions from the public. There is some.
In English. So first, thank you very much for a clear presentation. Very like it. So my question is, if I understand correctly, when you're measuring is almost gas phase, measuring temperature, and an excitation with a coherent laser type of experiments, right? However, in biologically relevant conditions, usually you are in room temperature, condensed phase, and exciting with incoherent laser sources, that is sunlight. So my question is, it's impressive that the experiments match the simulations, but if you can extrapolate the results biology.
It depends. Some of the intrinsic properties could be, but here it will be necessary to really understand how the microsolvation, for example, in a biological system is going to affect. But for that point, we are going to need more water molecules. Then from regarding the excited state, for example, excitations, it's going to rely on if, for example, in NO photodonors, if the carrier create like an isolated condition. Sometimes it could happen that it looks like an isolated condition from the carrier. So if you use the excitation there, it could be enough. But to be honest, I need to test that, or I need more information, not from me, another, I don't know, pharmaceutic PhD or something like that to really understand how it goes. But from here, we want to just propose a starting point. This is the set of molecules that you could use. And then, yes, you have to check for sure. Thanks for the question.
Okay, I enjoy very much your talk. First of all, I would like to say congratulations to you for your work and congratulations to your supervisors, because really an impressive work from my point of view, and with getting these kind of results, it's impossible with the developments we have here. So you have to make all this trip, and you have to be involved in this,
Learn
this kind of parts PhDs. It's a very, very nice work, and your presentation also was very, very nice. Just first, maybe a silly question. From your experiment, is it possible in the microsolvation experiment, is it possible to check if the water molecule is attached to a specific part of the molecule, or it can move around the target molecule, the water molecule?
Yes.
Is it possible to check that
From the experimental?
from the experimental point?
Just with experimental data, no.
Because theoretically you can check it.
Yes, that is the key for that point. But experimentally, no, because we are just following the mass spectrum. Mass spectrum, yes. So we are going just to see the masses, and there is no more information than that. Unless then, yes, if you get the spectroscopy, you compare with the calculation to really be sure about that. But then if with just one water molecule is challenging. But you could think or use your chemical intuition to predict, okay, it has to be there, and somehow in terms of properties, the molecule. But no more than. Thank you. Thank you for your question.
Okay, if there is not, okay.
Franco, congratulations.
Thank you.
It was a great talk. I have a question, maybe a silly question on experimental part. So if you can go to, I think it was slide 22, it was on the nucleobases with the silver complexes.
Yes.
The spectrum that you have band A and band B.
It's hard with this because it's don't move or move fast.
Yeah, any of this. So right next to band A, you have, it's like the baseline goes up, and you have what it could be another band that is very
You
close
say
to
here
your band A.
on this one.
On the bottom spectrum,
Yes.
right after band A, you go that, the first peaks there.
Yeah.
Can that be another more?
Yeah. From the beginning, if you see the spectrum, you could expect many conformers, and you don't know which one could be, and even as well could be many signature of the excited state. But to be sure that you have to go through this process, optimize the structure, know all the conformer possible in your experimental condition, and compare the vibrational information and the excited state information on all of them. That is something that I've done, but I'm not showing here. But I compare all of them to be sure that could be or not. But the main key of this is the infrared spectroscopy. When we observe the transition, it's okay, it has to be this one because just key to amino, and there is this vibrational movement specific of the group. But that is for that reason, if just with this, you could have some assumptions, but you are not 100% sure. With the infrared, yes.
The baseline is funny because it's very low.
Yeah.
At the beginning of the trip.
Yeah. Well, thanks for your question.
Thank you for the explanation.
Another one? Okay, if there is no more questions, we want to talk to say thanks to Franco, and then we kindly ask you to wait outdoors for the deliberation of the committee. Anytime. Voy a leer el acta de finalización de la defensa de tesis de Franco. Por todo lo expuesto, esta comisión evaluadora aconseja a la señora decana de la Facultad de Ciencias Químicas el autor del título de doctor en Ciencias Químicas con la calificación de sobresaliente. Y en este acto, Franco va a leer un documento de la Universidad de París-Saclay.
Yes, well, in the presence of my peers, with the completion of my doctorate in physics in my quest for knowledge, I carry out demanding research to demonstrate intellectual rigor, ethical reflection, and respect for the principles of research integrity. As I purpose for my personal career, whatever my chosen field, I pledge to the greatest of my ability to continue with maintain integrity and my relationship to knowledge in my method and my results.
Bueno, Franco necesita mostrar algo.
Yes. Well, I will do just briefly in English, just to thanks to all the people in University Paris-Saclay that I met during the last years, and Jean, Michelle, and Sachin, who really invite me to be part of the team, and they always be present for me for anything that I need, and they make me feel like home, because some parts to be outside is quite difficult, but they become friends and closely, as well as all the PhD friends that I met over there. And I share time. It was a pleasure to meet you and share our PhD over there. Ahora voy a cambiar al español. So here is the decisive group. Just thanks to all of them. I want to show that picture and that's it. But thanks to Benoit as well, sorry, Pierre, Nilufa, Ali, and all the PhDs. Ahora sí lo van en español. Gracias al grupo de Gustavo Pino, que comencé con él desde mi beca SIN como en el 2018. Llevamos mucho tiempo juntos y la verdad que ha sido muy bueno tener toda esta experiencia científica, la propuesta de tener investigación en el exterior y alcanzar ese nivel de tecnología está muy, muy buena, así que gracias Gustavo por esa vinculación. Después a mis compañeros, esta foto la sacamos ayer porque tenemos un nuevo integrante en el grupo y lo queríamos sumar, pero estos son los viajes que hemos compartido en congresos y demás, y la verdad que ha sido muy, muy lindo compartir tiempo con ustedes. Luego a mi novia, a Gianela, gracias por todo tu amor y acompañamiento durante todo este tiempo, incluso a la distancia. Luego a mi familia. Mi hermano mayor que está en Buenos Aires y nada, no pudo venir, pero yo sé que me ha estado apoyando todo este tiempo. Desde que tengo memoria, estamos juntos y nos apoyamos en todo y la verdad que se siente muy grato. A mis padres que, bueno, pudieron hacer el esfuerzo de venir hoy acá. Y la verdad que es hermoso tenerlos. Gracias por la vida y la oportunidad que me han dado. Lo voy a recordar siempre.
Gracias, Pancho.
Y también a todos ellos que son mis amigos, son mi segunda familia. La verdad que estoy muy feliz de tenerlos y que siempre, no importa cuánto tiempo pase, los veo y la foto sigue siendo igual. Estamos juntos y compartimos tiempo juntos y nos tenemos el uno el otro. La verdad que está muy bueno. Así que gracias por su cariño y el tiempo de siempre. Bueno, mis amigos del secundario que me conocen desde que tengo 15 años. Y nada, hemos ido evolucionando con el tiempo. Ya estamos horribles.
Como Pancho.
Mis amigos que también de España, que bueno, fueron mis primeros amigos en Francia. Well, here are all the PhDs that we usually met after the office, and that where we testing some food just for a PhD defense. It was amazing. It was nice to see all of you during this time. También agradecer a más amigos y más familia que he ido conociendo a lo largo de todo este periodo. La verdad que es muy lindo tenerlos. Gracias, de verdad. Y a mis abuelos, que nada, mi abuela, gracias por esos mates siempre que compartimos. Y a mi abuelo, que bueno, para mí es muy importante. Fue quien me guió mucho y me acompañó durante gran parte de mi vida. Él me enseñó muchas cosas que hasta el día de hoy sigo encontrando en mí. Así que nada, gracias, Leonardo.
Con tu corazón.
Te felicita, Leonardo.
Eso, eso es otra cosa. Pero, gracias.
Termina.